today to talk about geosynthetic reinforced soil integrated bridge systems. I know it's a long title, so we've abbreviated it to just simply GRS IBS. And essentially what we're going to be talking about today is trying to construct bridges, and it's really the bridge substructure that we're talking about, faster and at lower costs. Okay. And as most of you know or might have seen, well, I'd like to start real quick. How many of you have heard of GRS IBS? So almost all of you, just about. So you already have some sense of this, and primarily I'm guessing because this is the third round of Everyday Counts where GRS has been promoted. So we're starting again through EDC 3 to promote the technology of GRS IBS. And it has changed quite a bit, not the technology itself, but the knowledge or experience with the technology has changed quite a bit since our first round of Everyday Counts. And you'll see this in the photos and in the examples that I'm going to show you, and that James is going to show you here in a little bit on the projects that we've been able to build around the country. So just a quickly on the agenda topics that we're going to be talking about today. We're going to talk just a quick overview of what GRS IBS is. And since most of you looks like have had quite a bit of experience, I'll run through that fairly quickly. But please stop me if there is any questions that come up while I'm doing this presentation. An implementation progress. So we've been doing this for Everyday Counts 1 and 2. So what are we doing differently in Everyday Counts 3 that's going to help us get more bridges out there and standardize this practice a little bit more? And addressing some of the implementation hurdles that are out there. Why aren't you using more of these types of structures? So I'll try to get some feedback from you guys, but I'd also like to share with you some of the lessons learned or some of the things that we're doing to help address some of those hurdles. EDC 3 implementation. So what are we doing in the next EDC round? And then just talk about some of the example projects that we've done. I think those speak volumes as far as the types of projects that are being constructed, the different types of superstructures that are being implemented on top of these GRS abutments. Again, we're talking about a substructure, and there's all kinds of different superstructures that are placed and constructed on top of the GRS abutments. So I already asked that first question, how familiar you are with GRS IBS, and it sounds like you have some experience with it. Has IBS been implemented in your state? How many people have had experience in actually implementing the technology? So almost everybody in the room. And I can't see what's going on the website, but based on my experience and the map that I'm going to show, there's almost all of the states in the country have had some sort of experience using GRS around the country. If not, what are some of the barriers to trying this technology? So for right now, I just want you to think about that for yourselves. I'm going to bring up this question a little bit later on, but think about it now, and as I'm going through the presentation, I may be addressing some of your concerns. So just real quickly, what is GRS IBS? And strictly speaking, GRS is an accelerated construction technique for bridge systems that utilizes alternating layers of compacted granular fill and geosynthetic reinforcements. And the reason why it's important for us, and the reason why Federal Highways finds that is important enough to introduce it in EDC 1, continue it in EDC 2 and 3, is because we have had quite a bit of experience in savings, not only in time, but in money. The other benefit that I like to speak about, and I think it's an important one that we don't really talk a lot about, is that smooth transition between the superstructure and the embankment approaches. I think there's a lot of things that happen to the structure as far as maintenance and damage to the superstructure, as well as our vehicles, and as well as safety concerns when you have uneven riding surfaces across those bridges. So there is a lot of benefits in smoothing out that transition between the superstructure and the embankment approaches, not to mention the maintenance work that we need to do a year later to bring up the fill because we've dropped an inch at the ends of the abutments, right? So that causes more construction delays and more maintenance, people being out on the projects, and causes some additional exposure to traffic for workers. This cross-section here just gives us an overview of what we're talking about. What is GRS IBS? And what we're looking at is some sort of facing element. And most of these projects that you're going to see, we're using these concrete masonry units or the segmental retaining wall units that are fairly small. They're nominally about 8 inches by 16 or 18 inches long by 8 to 12 inches in depth. But you'll see in some of these pictures that we're using some larger block units as well as some panels and sheet piles types of facings. The facings themselves don't impact the stability of the structure. We can use whatever type of facing is required for the project due to the durability or aesthetic requirements of the project. So we can adjust the facing element based on whatever is required for the project. And we're going to talk a little bit more about the facing here in a little bit. The backfill material that's in here and the spacing on the reinforcement is what creates that composite material that we call GRS. And we're going to talk a little bit more about that. And we have another area in here where we have a slightly tighter reinforcement in order to get that load, those high loads from the bridges down deeper into the embankment and control those lateral deformations up near the surface. Then the integrated approach essentially acts like your approach slabs that you would be familiar with. We're trying to transition. We know we have new construction with the bridge and embankment construction that you see in this cross section, and at the end of this extent, there's no work being done. Therefore, there's going to be very little to no movement at the very end, at the area where we're not working in. So the settlement and the deformations that are going to occur, and they do occur, they always occur. Anytime you're placing fill, no matter how well you do it, you're going to have some sort of compression in that fill, and you're going to have some sort of settlement in the foundation soils. So all that deformation needs to be accounted for, and that is being accounted through that transition between that superstructure and that existing construction. What we typically do is put the bridges on deep foundations, but the settlement of that embankment is still going to occur. So we create these voids underneath our approach slabs, right? And those either need to get filled in, or they're going to settle, and then we need to bring them up, right? And that's what happens. And that's the type of maintenance that we end up doing, a year later or 6 months later after we've finished constructing these projects. This type of construction, essentially a shallow foundation type of project, all of this deformation that's occurring is happening uniformly inside that embankment and in the superstructure. So it all deforms together, eliminating that bump at the end of the bridge. And I have some really good pictures after a year or 2 years down the road showing that performance. In the cases where we have some softer soils in the foundations, or we're doing some water crossings, we're looking at doing a reinforced soil foundation. And that reinforced soil foundation, the purpose of it is to provide ground improvement and to be able to start off in a level, clean, firm foundation to get started, to start the abutment construction itself. So I mentioned in that last slide, we're creating this composite material. This composite material is very similar to many other materials that we're very familiar with using. Concrete itself is a composite material, right? Bridge engineers, most of you are bridge engineers in here, or have bridge experience, bridge construction, or have taken some sort of civil engineering concrete design at some point in your life. So we have concrete, and it's composed of aggregates, cement, water, aggregates and sands and different additives. And we combine this in many different ways to get different types of performance as far as ultimate strengths, a stress-strain modulus of the material. We good? And it is itself a composite material that is composed of these individual components. GRS, what we're talking about is we're creating another composite material that is composed of an aggregate, which is the fill material that we're using, and geosynthetics that are spaced in a certain way, placed and compacted in a certain way, so that it creates this composite that has predictable performance. And predictable performance meaning it has a certain ultimate strength or nominal resistance that we use in LRFD speak nowadays. So we have so we can look at our strength limit state, and we also have a stress strain curve that we can use for our serviceability analysis in our LRFD approach. So we take this concrete design, and in girder design, we take it and design our girders, and we come up with an area of steel that's required to provide the performance of that steel or that concrete girder. So we calculate this area of steel. Very similar to what we do with a GRS type of structure. Well, we can space this reinforcement for like an MSC type of structure at 32 inches, the maximum allowed in AASHTO, 32 inches, down to 8 inches, which is what we use in a GRS type of structure. And all of these types of structures which are reinforced type structures, are considered to have some sort of composite behavior. But it's just a matter of the degree of that composite behavior. How efficient is that composite working when you adjust that spacing from 32 inches down to an 8-inch spacing? When we do a steel design, we calculate an area of steel, we can come up with a certain area of steel that we can divide up into a couple of big bars, or we can divide that up into smaller bars that have more of them, right? And we do that to control cracking, to improve performance, there's lots of benefits in reducing the spacing of those steel bars in concrete design so that you get better performance, not only in strength, but in serviceability, cracking, deformations, and so on. So think of it, this is what we're trying to do with a GRS type of structure, is reducing that spacing to control the loads that are being applied to the facing element so that it has to carry less moment and shear across that facing element or panel. So at the point where we're talking about our 8, 12-inch spacing, the loads that are on the facing element are little to nothing, okay? And therefore, you end up with a much better alignment and better performing structure, as well as you getting better placement and compaction of your fill. So with that, we run some performance tests to try to determine what the properties are of that composite material. Because as we change the spacing, as we change the fill type, as we change the geosynthetic type, we have different performance. Just like if we change the water-cement ratio, or we change the additives in the concrete, or we change the aggregates, we have different performing concrete. So we have a whole bunch of curves that we use to determine what the properties are of that material. And we work down in this range of this curve. We work in the less than 5,000 pounds per square foot pressure for the bridge loads. And generally speaking, under 4,000 pounds per square foot. That's what our guidelines say, is less than 4,000 pounds per square foot. So we're down here in this range of the curve. So if you separate all these out with different types of fill materials, you start seeing those bands that are very tight at the working stresses that we're working in. So the deformations that you're getting are very, very predictable at the load levels that we're working in, okay? And we can use these curves to figure out what our ultimate strengths are so that we can do our LRFD calculations for strength limit state. We can also look at our deformation of these curves so that we can, at the working stresses, so that we can do our serviceability analysis. That's all the technical stuff that we're going to talk about today. I think it's important to understand that there's a lot of work that's been done in order to develop the design process. Obviously, we haven't gone through it all here, but this is the concept of how this is all working together. So since Every Day Counts 1, which is about 4 years, where we had 2 states that had 2 counties, 1 county in each, that had constructed maybe 20 or so structures at the end or middle of 2010, to now at about 192 structures, and there's actually more. I keep finding out about more projects as I go around doing presentations like this, but in about 43 states. So you'll see that before we only had maybe a few projects in New York and a few projects in Ohio. Now we have projects all around the country, and you'll see I've chosen a few projects to show you later on as examples, but you'll see that there are all different types of superstructures, all different types of design mechanisms, contracting mechanisms as far as construction, and it's working pretty good, and we're getting quite a bit of projects being constructed around the country. And one of the things that I'll talk a little bit more about this a little later, we're talking to a lot of bridge engineers. So in order to accommodate that, what I'm trying to do is bring in to this conversation some more experience, personal experience with the construction and design of some of these GRS bridges. So I've asked James Lupke here from Wisconsin DOT to talk about some of their experience on the projects that they built. James?
Well, thank you, Dan. First, also want to thank Dan and FHWA for his work, for myself to be presenting today on this project, successful project, and also kind of going back to the FHWA's administration about it was included, GRS was included in 1, 2, and 3, and Wisconsin's a good representation, and we still need that extra little push to keep this going and a little bit more assistance before it's fully implemented. My name is James Lupke, work for the Wisconsin DOT. I am a development engineer working on policy and standard items. And over the past couple of years, been getting integrated into our geotechnical unit more and more, specifically MSE wall, and of recent been taking on this GRS IBS point of contact type lead for the state. So very excited about this, and kind of the outline of the project is going to revolve around our one project that we have completed. I think you might have saw in our picture we had 3. 2 are currently in the design phase, and we're excited about that. So it's going to revolve around our one project that we have completed, how we got to that point, and looking for that next GRS project and the tools and process we're going about to find it. Also want to include just like our ABC technologies in general. We're moving forward with a lot of different things. The Rawson project was one one thing I was involved, Rawson project, very exciting project, where we had 2 spans moving with the SPMT over I-94 traffic. Very exciting. And then our precast pier initiative. I mentioned those just because of the partnering included in these projects, and get the word out and work with many different entities. Relates back to our initial GRS effort. And that's kind of our other initiative is GRS moving forward. In 2012, we completed the first GRS abutment. And also in that year, we rolled out ABC Chapter 7, including ABC Works. Both of those documents were largely with the help of FHWA and the resources they provided. And then 2013, formed ABC Bridge Team to more act as a steering committee for when there is a GRS project or ABC project to come in there to assess the value and maybe integrate it to elsewhere and provide a technical support. And also rolled out 2 different standard details for GRS abutments, very close to what FHWA has out there right now. And this past year, we were in contact with UW-Madison as far as the monitoring of that first GRS project and looking at how to refine it, lessons learned, moving on to the next project. So our project consists of State Trunk Highway 40, about 3 hours north of Madison, over Hay Creek. This is a completed bridge structure. The existing structure consisted of a 20-foot span timber abutment, very prevalent in Wisconsin over the waterways, substandard rails and traffic conditions. It was slated to be replaced in 2012. Already in the program, with this ABC initiatives, we thought it was a very good candidate based off of several different parameters. But mostly get it out there, see if there's a cost saving, eliminate that bump, and with FHWA's help and UW-Madison already in line for monitoring, seemed like a good fit. So as we approach this project and as we're approaching the other projects, 3 core areas we're looking at. Hydraulic units, we'll be assessing waterways. We feel that hydraulics are, a good bunch of these bridges will be hydraulic related, just due to the amount in our program and the ones that will be replaced. And then our foundation unit as well, putting in their input and bring it together with layout and other parameters. In our ABC rollout of Chapter 7, we included 12 different set of criteria to lead the designer in whether this GRS was a good candidate. Hydraulically, this site was acceptable, so was foundations, and as far as roadway, there was 0 skew, and the waterway was relatively perpendicular to the structure. The project had begun through preliminary and almost to final design with a pile encased abutment, our traditional product that we would deliver. We went back and asked for a redesign and had a very quick redesign since due to simplicity of the structure, added the abutments, very similar to our MSE wall type delivery, and worked with Dan Elzamora with the specifications, getting those up, and then looking at other states' past work. Let the project as our typical design bid build, and selected the contractor selected a system, and we subsequently reviewed the shop drawings, and the Northeast administered the project. So some existing pictures, downstream, upstream. The thing to note, this project was tied to a larger project. For this one, it was about 500 feet of reconstruction. So you can kind of notice it's on the bottom of a sag where the river is. And we subsequently raised the profile about 1 foot at the bridge structure. And will become a little bit important later on, but the bridge was on the critical path. So as soon as we could get this bridge open, road work was all ready to go and can open up back to the public. So as I mentioned, very good layout parameters. Superstructure, we from the traditional design, we widened it out 5 feet for several different reasons, but very simple turnaround for redesign, flat slab bridge. The unique thing about this one is we decided to go with a cast-in-place flat slab. I believe it's one of the first ones to use this superstructure. And with that, we utilize the existing piles, timber piles, for supporting the false work of the superstructure. We had recommended that, and that's what the contractor had proceeded with. So construction started in end of April 2012. Here's a picture of the reinforced soil foundation, and then the wrapping material going over that once we're up to a certain height. I believe in this one we had a rain event prior to or during the excavation, and was able to mitigate any delays with this site, let the water drain out, and proceeded as pretty quickly right after. And this is the first layer of reinforcement going up. We used a modular block similar to our modular block retaining wall system, the false work system, and then showing a detail of bearing on top of those existing timber piles, and then pouring of the deck. So the completed bridge, I believe it was in end of early June it was completed. So drove the beam guard posts, metal posts through the grids. And for benefits on this project, reducing the construction time. Our typical project would probably be around 60 days. We're able to reduce that down to 37, and that's with the cast-in-place superstructure and cast-in-place parapets. So there's definitely some time savings we can squeeze in there. Less complex project. For this one, I believe that a landscaping company put in the retaining wall, so you're not having your skilled laborers out there, and not requiring your pile driving techniques. And so mention on the weather was flexible. For bridge monitoring, we had UW-Madison come out there and put on several different sensors throughout the deck and the walls and area around it. Been monitoring for the past 2 years. Here's a picture of a settlement plate and one of the wall reflectors, and had some on top of the wall as well. Met with UW-Madison earlier this year, and preliminary results are fairly good. As Dan said, there will be displacements, and we saw displacements, but nothing that got us to a level or were concerned with. They were just expected. Some displacement, a little bit of differential movement, but nothing of too concern, and which was reflected back onto the substructure and superstructure as well. The one thing that was an oddball, and Dan's probably not glad that I'm mentioning it, but we did have some approach issues with a heaving type event with the approach, where the approach rose above the deck. We're looking at that right now and trying to calibrate some of the elevations and see what part did move, and look at what we use for gradations and other things. But as a result of that, we saw no signs of distress in either the deck or the approach. Both are working independently of each other, and I would think that if this is independent or could have been amplified with a deep foundation where your structure's there and your approach is going to come up and down on that paving notch, it may have been a worse scenario. So, or see what the final results indicate and go from there as far as elevation control. And here's some pictures on that heaving event. We had 2 winters, and both events did show some movement coming up. And just last week went up there and relatively level. So we're having a seasonal type bump condition on this location. And it also seems to be problematic throughout the actual whole approach beyond the reinforcement. So it's the whole subgrade system. We did raise the profile a foot at the bridge with dense aggregate as your primary subbase. And here's some of the UW-Madison results with the heaving event during the winter, the 2 past winters. And the magnitude is around 3 centimeters. So there was a field inspection had indicated some minor cracks in the structure. And with the amount of people on this site, with design chiefs, administrations, there's going to be some cracks. When I went out there, I had these pictures before, blew up the location of them. It's hard to see, but I was literally crawling around to find where these cracks were. They're very minute, and this one is located at the 3rd point of the bridge, so nothing of concern flexually, just cracks in the bridge. Another interesting thing after the fact, we are located in the northwest area of Wisconsin, and the gray area, we're right in the heart of the frac sand formations, and all the red sites indicate mines. And it was through the UW monitoring team, they kept on saying there was a lot of truck traffic, just trucks flying through there all day long. And sure enough, I went and looked and found out that State Trunk Highway 40 is right on a frac sanding hauling route. So a lot of loads coming through here. The ADT is around 1,600, but mostly truck traffic. So a little picture of the little video of the trucks, empty one coming one way, and looks to be a fully loaded truck coming the other way. And that was throughout the whole time I was there for half an hour. I lost count of how many trucks were actually going through there. So as far as loading, I think we'll see some good results of comfort level of putting trucks on there and getting that ADT up. And for comfort level of the state overall, no signs of distress with this truck traffic currently. So works in progress. We had the first showcase, I believe the first showcase nationally as far as GRS getting it out there. We took that opportunity with a bunch of folks, and then also took it on to our other groups, county commissioners, and just spread the word about GRS possibilities. So taking around, talk to different clients. Our primary client or interest is that local road program where they have tons of short span bridges. They've shown some interest of getting this into their program as far as maybe using their county forces to do the work, not requiring the deep foundations. And we've been providing technical support to those local officials, consultants who have come and asked about this technology. So we're mostly just spreading the word right now. And we've also indicated to our in-house design and our other scoping tools this is a tool. It's an opportunity to, if there's a right location, we should definitely look into it. And that's our feeling with this project. It's just a tool, and if there's a right location, definitely we should look at using it. Not for every location. We've only had one in the past 2 years, so we're hand-picking these, and they'll come in when they're ready. That's how we're approaching. We're not going to go to a county official and say, let's do one here. We want it to come from them rather than a top-down type approach. Moving on for future stuff, obviously the cast in place is not ideal with the ABC initiatives of faster emplacement. So we're looking at resurrecting our precast box girders, improving some of those joint details, and mitigating some of that reflective cracking that we're seeing on our old details. Several different approaches on that, but that's kind of our next focus for getting that up to speed. And also the package with just keeping it simple, whether it's railings or other things that would be advantageous for landscaping or less skilled crew to come in and install. That's kind of what we're keeping in mind. We won't open to cast in place as well, and just keep on upgrading our backfill materials and other specifications, look at that approach stuff. That heave issue is, I think we kind of take it as an outlier of results, but not directing us in backwards. And also take it kind of full circle, round trip it back into our MSE wall usage. We do a lot of MSE walls in Wisconsin. Deep foundations are always required for our superstructures. So we want to see if we can maybe integrate this technology as far as bearing locations back into MSE, and if the site's locations are right. And then future on scoping efforts, maybe it's in the program level of identifying these sites that are good candidates early on in the program and before they come up to a consultant for redesign. So getting ahead of the game. So the next project is to make the three projects up on Wisconsin. We have one here up in, I think this is Dodge County and Barron County here. This one in Dodge County, we've done 2 iterations of scour control. As you can see, the water level is fairly high. No white caps or anything. It's relatively low velocities, but we've done 2 iterations of scour control just to make sure all the floodplains, defer it back to my hydraulic units, but we're very involved in that process for moving on to the next step, and that's what it's moving forward with GRS potential, as well as the other bridge project, and fielding questions as a technical support for folks out in Wisconsin. More information, there's a YouTube video of this showcase project for GRS up in Wisconsin, a good representation of that project and interviewing a couple folks. Dan's even in there, giving a little blurb. And then WISDOT Bridge Manual has some more information on GRS usage, ABC usage, and maybe take a look at our 12 different criteria that we use for establishing whether it's a good candidate or not. And then, as always, FHWA guidelines. Just like to thank Dan Elzamora for his help in the past and his technical support, and then also Bill Leva. He kind of led the way and handed off to myself, and just some other numerous number of folks that I'm not going to mention, but it's been a great process thus far, and we'd like to continue. So with that, give it back to Dan.
Any questions for James at this point? Okay. Go ahead.
Yeah, you mentioned scour, but I guess I'm not certain yet without asking the question. What special considerations or concerns do you have regarding scour because you're not building a deep foundation? Are there any special checks or certain situations you would not build this button type in?
Speak on half of the hydraulic units. We've gone in as far as making sure there's that the foundation, the reinforced soil foundation, is below the scour depth, whether it's the critical scour location, and providing the proper armament on top of that, and then kind of going through those what-if scenarios. We're hesitant as a DOT and talking with Dan, try to get some more comfort level, but we're looking at those what-if scenarios. Maybe it's a pressure flow and the scour goes deeper. We're looking at kind of all different parameters. It's a little bit different for us, so we don't have that luxury of a deep foundation to say it's okay. So it's out of my kind of comfort level of hydraulics. That's why we put it back there, but that's why it comes back to the site locations. We keep the velocities low, capacity low, and then going through that scour analysis.
And I'm going to address that specific issue here in a few minutes anyway. So I will come back to your question with a much more sensitive discussion. So was there a question from? Oh, Mike. Sorry. Were there any other questions for James? And I'd like to point out, I'm not afraid of showing some of these issues. I think it's important to learn from these experiences that are happening in the field. This issue with this essentially a reverse bump at the end of this bridge because the embankment actually went up instead of going down is an important one to learn, and it has to do, I believe, I'm sure Wisconsin University of Wisconsin is going to be looking at this a little bit closer. But my thoughts are on the type of backfill material that was used the fill that was used in that embankment, which I think might have been had a little bit of plasticity in it and had some expansive characteristics in it, and which is what's causing this issue. At least that's my theory behind it, but I'm sure we'll have a lot more information. They're writing papers and presenting them. But the point being that experiences like this, it's not something that we should shy away from. It's important that people understand that selection of materials is important, and it's important to learn from these experiences. So I think the project overall is excellent. I mean, the truck traffic that was added to that project was significant, a lot more than what was anticipated in the original design, because of the shale issues that they're encountering, and the bridge is handling that additional loads with no problems at all. Thanks, James. So again, what is the biggest impediment to implementation of the GRS IBS? Obviously, we've heard about scour. Do we have any pens over here? Does anybody have any? What other things? Hang on. I'm supposed to turn these on.
From Oklahoma's standpoint, it's just the labor pool that's hard to come up with there for our local agencies.
So, Oklahoma mentioned the labor pool, and when you say labor pool, mean the skill level or the number of people?
Number of people available to work, and then also the age of the workers. A lot of times the older workers don't really want to do this type of work, or can do that with bad backs or whatever. They're better off running a grader or driving a dump truck.
Right. So the question is the number of people and the age of the labor pool that's out there. Anything else?
In Kansas, we're still scared of the hydraulics.
Okay, so in Kansas, the concern is the hydraulics, and obviously leading up to the scour issues, the potential scour issues that are associated with the hydraulics. And as I mentioned, I will bring that up specifically. Anything else out there?
Possibly the long-term durability of the unreinforced facing blocks.
Okay. Durability. So the other concern was durability of facing blocks, and I'm also going to address that one specifically here in a minute. Anything else? Well, there'll be more opportunity here in a few minutes. Was there anything out on the web? Okay. Those are all good concerns and good issues. And we have been dealing with that for the past 4 years, and those are some of the biggest impediments that we're dealing with. This is the first time I've heard about the labor pool and age and number and age of people, but I can see how that could be an issue. And we'll talk about that here in a minute. So here are the primary ones that just from my experience of working on this effort for the last 4 years, the primary ones that I have seen, and the ones that we're going to address through this presentation, then we'll talk a little bit more about your issue, have been these. The use of shallow foundations primarily related to the settlement or serviceability of the structure. Okay, so deformations are always an issue. And I always hear, we want no settlement, or we want less than 1/4 inch or 1/2 inch of settlement, or zero settlement, I've heard. And zero, we don't do zero. I can't do zero. So settlement is a big issue. Scour of abutments at water crossings. So that's something that we're going to talk about here, and that's probably the biggest concern, especially in these water applications. Facing durability, I think, is a close second or third in there with the serviceability issues. And then seismic performance out here in the Midwest area. I know Missouri has some seismic zones, some pretty strict seismic zones. And a few other parts in the East Coast have some seismic zones. But primarily, this issue comes across more in the West Coast type of projects, out in Washington, Hawaii, California type of projects. But we're going to talk a little bit about that here. So let's start with this one. Okay, shallow foundations as it relates to tolerable deformations. In the past, we used to do a lot more shallow foundations than we do now. And in some states, we still do quite a bit of shallow foundations, especially shallow foundations on bedrock type of foundations. But even some states do shallow foundations on soils foundations. The concern primarily has to do with deformations, at least when we're not talking about water. The amount of settlement that's tolerable for the superstructures as it relates to what we're going to be able to get out of our foundation elements. When we're talking about single span structures, we have quite a bit more tolerance of the deformations. And from what our observations have been, the deformations haven't been differential settlements. They've just been fairly uniform settlements across the superstructure. So we have, I'll show you photos of one bridge. It's almost 3 inches of total settlement. And you mentioned 3 inches to some people, and 3 inches is a lot of settlement. But when we're talking about a single span structure that's 140 feet in span length, the angular distortion that's associated with that 3 inches of settlement, even if it was differential settlement, would be very negligible. Okay, and the structure itself wouldn't feel that differential settlement. Wouldn't know that it's moved. But in most cases, it's 3 inches of settlement, but both sides have settled, including the embankments. So really, nothing has happened to the structure itself. So federal highways has been, generally speaking, not just talking about GRS, but talking about shallow foundations, has been trying to encourage or show that the performance and the behavior of shallow foundations, and trying to get people to start using them again in the right applications. So we have put out some publications that talk about the performance history for many, many years, and there's quite a bit of research out there on performance of shallow foundations. And also some guidelines in looking at some of these issues associated with shallow foundations. Part of it has to do with we're just not used to doing shallow foundations. In many states, we're just not used to doing them. And I was talking to James, in Wisconsin, and in many other states. I know for a fact we'll drill in piles into bedrock, just so that we can put our deep foundations through our MSE structures or through our embankments. And because we don't want to set our structures on shallow foundations, we want to put them on bedrock or on something firm because we want to limit that settlement. So I think there's quite a bit of opportunity there, generally speaking, in using shallow foundations. But GRS IBS falls into that same category as a shallow foundation. It is exactly the same same design approach. In this particular example, we have a project in Illinois. We're going through 20 in Illinois. Somebody was here from Illinois. This is but I believe it was 20 feet of organic soils, organic clay soils underneath, very soft materials. They ended up putting some stone columns for ground improvement underneath, and we're monitoring this structure. And this structure settled maybe about an inch of settlement. It's a pedestrian crossing bicycle trail on top, but as you can see, it's got 4 ASHTO girders on a 12-foot wide section. So it's a fairly heavy structure, okay? I mean, this is almost an interstate type of structure that you're seeing here, even though it doesn't have that traffic. It's designed for HL93 loads. It's a fairly significant load that's being designed for. And we've had very little settlement on this structure. The ground improvement worked very well. The reinforced soil foundation that was used acted as a load transfer platform between the ground improvement and the embankment approach, which transferred the load very efficiently across that section, and it's working very, very well. This is a picture I took just maybe a month ago, and there's no cracks, no bumps across that joint. It's been in service now for at least, I'd say, 3 years or so, and it's working beautifully. And by the way, these are some of the large blocks I'll just start mentioning here, okay? So these are a particular manufacturer that was used, but they selected to use these large wet cast units as far as a facing element. We'll talk a little bit more about that here a little bit. This project is that 140-foot bridge, which is the longest span that's been constructed using GRS. And this project is on over-consolidated clays. And anytime we start seeing clay soils, we're thinking, well, we're going to have a lot of settlement, and we got to go immediately to deep foundations. Well, when we'll put it on deep foundations, and you'll still get a little bit of settlement, but very small. But your embankment will still settle based on that based on that clay soils and the load that you're applying. So you end up with that bump at the end of the bridge, right? In this particular case, they ended up with 3 inches of settlement, and I'll just go through these real quick here. So you ended up with some foundation settlement, and the red is the south abutment and the blue is the north abutment. So you can see the foundation settlements are fairly close. Even though they're not identical, the differential settlement between south and north abutments are very, very small. The bridge doesn't know that that has happened. The total settlement is almost 3 inches. But again, they're fairly uniform across from one side to the other. And this is the compression that happens within that embankment fill due to the bridge loads. Remember, the bridge is sitting on the GRS mass, not on the facing. So the facing is going to settle differentially from the embankment. So that's what this is, and we need to accommodate that differential settlement inside the details of the analysis, which we do. We just need to recognize that we have these different components of settlement that we have to account for. And this is almost 4 years of monitoring. A couple important things to look at here is, again, the uniform settlement between one side and the other. And it's not only from one north and south, but also across that same abutment. The settlement within each abutment was very uniform. Most of that settlement occurs initially when you place a superstructure, even before you place any placement, finish the paving, is what I'm trying to say, on the approaches. So it ends up working very, very well. Then we take that field information and we compare that to all those stress strain curves that we looked at before. So we take this number in here, which is that compression that we get inside that fill due to the bridge load, and we take that to our stress strain curve that we get for that composite material that we looked at earlier, and we plot that on that curve, and we can see how accurately we can predict that deformation based on the loads that we are applying. And this is a very heavily instrumented structure that I was just showing you. So you can plot that bridge right on that curve and see that the settlements that we're observing in the field are consistent with what we would predict in the laboratory. And we've done that in several projects around the country. And we're still monitoring. And as far as deformations, we're trying to get rid of this bump at the end of the bridge, and we're looking at running profiles across between the embankments and the superstructures in order to get a quantitative observation of the differential settlement between the embankment approaches and the superstructure. So on the left here in this red graph is a bridge with a deep foundation, and you can clearly see there's a bump at that end of the bridge, and you can see where the bridge starts and ends, or starts in this case. And on a GRS abutment or in a shallow foundation structure, you have a very hard time seeing where that bridge begins and ends. Okay, and that's what we're trying to get to, is try to get rid of that bump. On that 140-foot bridge, these are pictures of the striping across that. These are original stripings after 4 years of construction. Other than not doing a great job on the joint filler, there is no cracks or bumps or compression seen on these approaches. Even with the thermal cycles, which is another question that we often get in some of these areas. The thermal expansion and contraction of this structure, which could be a magnitude of about an inch, is not reflected in this structure at all, even though the fill is compacted right up against that superstructure. Okay? And without any joints. It has seen quite a bit of flow, including some pressure flows, as you're talking about, James. And even with all of this, and this hasn't just happened once, it's happened a few times over the past few years. And the most that they've had to do is go back in and do some maintenance as far as clearing all the debris that's collected underneath. And in some cases, repairing some of the instrumentation that's inside the girders. But there's no damage on the blocks from impacts from trees or rocks or anything coming down, which is another of the questions that we get. There's no cracks or bumps or anything on the superstructure or on the approaches. The structure itself is working very well, even though it's had some fairly significant events. This is another project that's in Maine, and in this particular project, it's a tidal type of fluctuation project. And in this project, they have about 12 feet of tidal fluctuations every day. So if you can imagine building something when you have 12 feet of water changes every single day, you only have 3 hours to construct this every single day during low tides. And every single day, your entire site is underwater for most of the day. And as you get higher, you get a little bit more time, right? But again, these are using these larger blocks, I think that somebody's asked me about, these larger block units. These work very, very well as well.
Is that a two-span structure?
Yes, and this is one of the few two-span structures that are out there, and this is on an island off the coast of Maine. And the reason, my understanding, the reason that they selected to go with a two-span structure versus a 100-foot span is because of the cost of shipping the precast elements out to the island. They decided to go with a 60 and a 40-foot span. And they decided to reuse that center pier, which was the original pier. And the big blocks here kind of mimicked the big granite blocks that they had used originally for that structure. And they used twin T type of supers right here. So it's a little bit different type of superstructure that you see on this project. But you can see how high the water is in here. So every day you have to deal with this. And they were able to build it fairly quickly and efficiently. So let's talk about hydraulics. I need water for that one. Okay, so hydraulics is it's a real, scour is real, scour is a big concern, scour is the reason why most of our bridges fail. We know that, right? So having said that, you know, this application is no different than any other structure that we build. We have guidance that's existing from federal highways, and which AASHTO refers back to as far as how to evaluate our hydraulics, how to evaluate scour, how to analyze for scour, and how to provide countermeasures for our structures. So our guidance in the implementation guide for GRS IBS refers back to HEC 18, 2023, in how to analyze the hydraulics and do the scour calculations. But it also talks about how to do the interpretation of what's in there and how to use the guidance. Okay, so it's important to go to the implementation guide that will then refer you back to these references, okay, which is what we all use, right? So the main thing to come across with this slide is we're not changing any of the practices, we're not changing the requirements. It's everything that you're used to doing for your states, for analyzing hydraulics, evaluating scour, and providing countermeasures. If you were doing it already, you're going to continue to do that for a GRS IBS. It's not changing anything. Okay, so that's the main thing. And our hydraulics folks like to point out that they do have quite a bit of guidance is available to download at their website under our FHWA hydraulics site. I'm pretty sure that you can just Google any of these and it'll pull it right up. There's also a scour calculating tool in this toolbox that they have available. So just want to make sure to point that out. So as far as the design considerations for hydraulics, these are the types of things that we need to look for. And it's the same exact thing that we would be doing for any type. If we're doing deep foundations or we're using shallow foundations, we're still looking at the design event that we need to design for and develop the criteria for that project. Adverse flow conditions, we need to look and consider those in how we're evaluating the hydraulics. Channel stability, which is important. Is that channel going to stay where it is? If it's migrating all over the place, we may not want to do a GRS abutment or a shallow foundation in that situation. Potential scour depths and foundation elevations. So we come up with what is our foundation elevation based on the calculated scour depths that are evaluated using HEC 18. Design scour countermeasures based on HEC 23. It's exactly what we would do regardless of if it's GRS or a shallow foundation or an MSE wall or deep foundations or anything else. Okay. HEC 18 talks about when we start off with is determining design flood frequencies and doing a risk-based analysis, and allows you to consider as the owner that risk-based analysis, which lets you evaluate cost versus risk, right? Do we need to design an interstate facility when we only have an ADT of 10 or 100 or 400 versus thousands of an ADT of thousands? So that is a decision, obviously, that you as the owners and the folks that have the maintenance responsibilities of these structures have to make those decisions. But you have that ability to do that. It specifically states that in HEC 18 as guidance. We also need to consider these types of adverse flow conditions. Adverse flow conditions, you know, almost every single case in here could be adverse. You know, almost every single project that's built can be considered adverse flow conditions. But you need to look at, you know, the consequences of having those adverse flow conditions and what are the hydraulics associated with with these conditions and incorporate those into the analysis and run the appropriate calculations and maybe a more sophisticated type of analysis in order to evaluate the geometries in that site-specific design. And at the end of the day, we also need to review the channel stability, right? We want to make sure that that channel is staying and it's consistent and it's going to stay where it's at. So once we have our hydraulics, we know what our elevations are, we know what our velocities, we know what our volume of water is flowing through there. We can, and that's all based on the hydraulic analysis that's already been done that's specific to that site. We can come in here and look at calculating the scour, do the scour calculations. And we need to calculate the long-term degradation, which would happen regardless if there was a bridge here or not, right? This is something that's just going to happen over time, regardless of anything being here. Then we're also going to be looking at the contraction scour. And the sum of those two values is the depth that we place the bottom of the abutments at. Now, if that depth is 5 feet in clay soils, it's very easy to excavate, and it's very easy to place. It'll be very efficient construction-wise. If this is 10 feet in loose sands underwater, you might want to reconsider doing something different, okay? So it's a site-specific decision as if a GRS IBS type of structure or any shallow foundation is appropriate for that site. So it's hard to say, 3 feet per second and anything under 3 feet per second will work. Well, maybe, maybe not. What about 5 or 6 feet per second? It depends on the types of soils that are underneath. If we have a bedrock foundation, hard granite bedrock that we're sitting on, is 10 feet per second okay? Yeah. I mean, it could be. You'd have to look at that analysis. You have to make those decisions. So we calculate that depth of scour and we place that bottom of that wall at that depth of scour. So we've already done part of that work. Now we need to protect those abutments from local scour. And we do that by using HEC 23 to design an appropriate countermeasure for that structure. And we place it about a foot below that bottom of the calculated depth of scour. That's where we start the countermeasure design. And this is consistent with what's in HEC 23 right now in Design Guide 18. So if you go to Design Guide 18 out of HEC 23, that's what you see. And it gives you this geometry. Now what happens is, in many of these structures that are 20 feet, 30 feet, this geometry ends up overlapping. And you end up pretty much with a full channel protection in here. And you'll see that in many of the projects that I'm going to show you as far as photos. You just end up with full channel protection. As the bridge starts widening and widening and widening, or the span length gets longer and longer and longer, they don't overlap anymore. But when you end up with, say, a foot, couple feet, 5 feet, you make that call of opening in here, you might as well just fill it in there, okay? So what we've gone over is, Federal Highways is not asking anybody to make any changes to our current guidance or practice. We have existing guidance and practice for hydraulics and scour evaluation. Use this information to see if your project is consistent with that and if it makes sense for your project. If it makes sense, it will be a really good project for you. If it doesn't make sense, then go use one of your other techniques. Just consider it and put it into the mix and see if it works. If it doesn't work, use something else. If it works, it should be a really good project for you. Any questions on what we've talked about in the hydraulics part of it? Because this is a big chunk and it's an important one. Have I said anything new that you wouldn't be familiar with or you wouldn't normally see?
Just that full channel protection there, that's interesting concept.
Yeah, I mean, that's, this here is current guidance. Okay, that's exact, that detail of 3 times D50 with, 5 feet minimum, and that 3-to-1 slope, those are existing, what's in there right now. It just happens that, if you have a 20-foot span and you have a D50 that's a certain size, you end up with full coverage. At some point, you start spreading out enough, and you could cover that up. If you have only a foot left there, you need to consider that and just fill it in. It's probably easier to do that. If you have 5 feet, you might still want to do that. If you have 10 feet, you may not want to do that anymore. At some point, it's a change.
If you have a inundated condition of the substructure and the water drops, does that backfill get saturated where you have to consider a drawdown and a hydrostatic pressure?
Yeah, the question for everybody is when we have a channel that fills in with water and it saturates the fill, what happens when the channel comes down? Will we end up developing hydrostatic pressures in the embankment? Well, that's the reason why for water type of crossings, we strongly recommend that you use an open graded type of fill, like what we would call an AASHTO number 8 or 9, between an 8 and actually between an 8 and about a 6. So an AASHTO size is between 3/4 of an inch down to about 3/8 of an inch type of aggregate size. That is a free draining material that has the particle sizes are big enough that they won't wash through the face, first of all, so we won't lose any volume through that face. The other thing is that as water comes in, water will escape as the water drops in front of it without building up any hydrostatic pressures. That fill also has the characteristics that it's not impacted. The friction angle or the strength or its shear strength is not impacted by water in that structure at all. So as water comes in and out, it's not going to impact its stability at all. So that's the reason why we would suggest that you use an open graded type of fill for these applications. Okay. Now, when we're doing grade separations, you can use a standard structural type of fill, or you can use an open graded material like these materials that we're suggesting here. All right, facing durability. These dry cast modular blocks have had mixed reviews in the past, and there is quite a bit of recognition, not only by us but by industry, that they've had some issues in the past. Since they started, they went off and started building modular block walls all over the place when they first started coming out. And they ended up with a lot of issues, okay? And they didn't help themselves at all in when they went out and started doing this. Since then, this issue was recognized, and there was a pool fund study to deal with this issue. Some of you might have been involved in, or some of your staff might have been involved in working on this pool fund study that was managed out of Turner Fairbanks. But trying to develop what are the characteristics and the specifications to give us a much better product that we're going to be building out there. So since then, the specification that's being used and that's in our FHWA guidance for MSE walls as well as for GRS addresses that durability issue and the concern that we've had. Now, there's many states that take that durability specification that's in MSE walls, like Wisconsin does, and adjust that specification and either makes it more strict or might lighten it up. It primarily has to do with these freeze-thaw issues and salting of our roads. Okay, so those are things that cause problems to these dry cast units. So if we're in Florida, where we may have some salts, in seawater, but we don't have any freeze-thaw cycles, it's not so much of an issue. If we're in Wisconsin, where we're salting roads and we have lots of freeze-thaw cycles, it's a more severe issue. And in Wisconsin, they have a much stricter specification for their blocks than even the FHWA guidance. Okay, and Minnesota does as well, and other states do as well. So you can deal with the durability concerns by specifying the appropriate materials for your specific climate and site conditions. And there is quite a bit of guidance out there. The only thing I'll say about specifying block durability, if it's something new to you in your state and the market, the producers of these products are not used to fabricating these kind of blocks, like. I'll just leave it there. But if they're not used to manufacturing those types of blocks, then you're going to have a learning curve, and you're going to have some issues initially trying to get block manufacturers to produce blocks that are at that higher level. Okay, that's happened here in Missouri. Anybody here from Missouri? Yeah. So that happened here in this recent project, which is the reason they ended up with these large blocks on the project that I'll show you here in a few minutes. So they imported those from Minnesota, but they could have imported the dry cast blocks as well from Minnesota. But that met the specifications. But so I guess just to finish up, try to find something that's appropriate for your conditions, that are consistent with what you need to have a durable product for your project. But you also need to think about what's available locally preferred. If you recognize that you don't have those products locally, you need to see if you can get them somewhere else and where you might be able to get them. Okay, and they are available. It's just a matter of finding them. And if you have those kind of questions, just give me a call and we can talk about that a little bit more specifically. The other thing is, we don't just have to use dry cast units. We can use wet cast blocks, these large wet cast blocks. I've recently found out that there are some smaller wet cast blocks, although they're not very common, so that's another alternative. Now, one thing I will say about wet cast blocks, the wet cast specifications for durability, if you stuck a wet cast block into a durability freeze-thaw testing that a dry cast block is being tested to in Wisconsin, let's say, because I know in Wisconsin, those wet cast blocks would not meet the specification for a dry cast block in Wisconsin, because it is that severe of a test. You end up basically with about an 8 to 10,000 PSI block. It's about 80, 85. Yeah, I recognize you don't want to lift up an 80, 100-pound, 1,000 blocks of 80 pounds. It's a challenge, but it is done. The issues associated with. Can you watch the time for me? Where am I in time? Good. Yeah. Panels and sheet piles are also an alternative. The issue is the impact on cost and constructability. Dry cast blocks are smaller units, and you have to place a whole bunch of them, but they go really, really fast. They really do. They're not that hard to build. I've done it myself, so I personally can say that it's definitely heavy duty work, and you're gonna come home sore. But you try to pawn it off as a good gym membership for a few weeks. But we have done sheet piles. This is a project in Iowa. where they do sheet piles on a regular basis. So it's something that they, in their own equipment for the counties, have that equipment to install sheet piles. So they decided to do a sheet pile facing. There's some benefits to doing that as well. So, there's maybe an increased cost in the facing, but reduce the amount of fill and excavation, and provided the scour countermeasures as well in doing this approach. There's a project in Colorado. They decided to do a full height panel, wet cast, precast panel type of structure with geogrid reinforcements. So that's another alternative. That precast panel is typically going to be much more expensive than a concrete masonry unit or a segmental retaining wall unit. But those are the decisions that you're balancing out as far as what you need for the project. And these are the large wet cast blocks that we've talked about already. And even in the block units that we have available, we have many different types of blocks. This is that Wisconsin project that James was talking about. There's a project in Utah that used also segmental retaining wall blocks. That's that Interstate 84 project. And then some of the solid blocks or hollow core concrete masonry unit blocks. So there's lots of options available. So what I'd like to leave you with as far as blocks is first get your material specifications that's appropriate for your site. Get the aesthetics that you need. If you're in a river crossing and the snakes are going to see it, then it doesn't really matter. If you're in a urban environment in a grade separation structure or a trail crossing where you see a lot of people will see this wall, you don't want to have a flat face concrete masonry unit. It's going to look ugly, and it's going to not going to be a nice project. So some aesthetics consideration would be appropriate for that type of project. So first pick the durability, material specifications, and aesthetics that you need, and then put that in the specifications and let the market find you the product that's locally available for you. Okay. As far as seismic, I won't spend too much time on this, but just to unless somebody has some specific questions on seismic, but the seismic, we have guidance in there, talks about seismic, and we know that we have really good performance on these types of structures with seismic, not only from large-scale shake tables, and if somebody's really interested, I can show you some a shake table test as well for that, we do have really good performance, not only from laboratory tests, physical testing and modeling, but as well as evidence from post-event inspection of structures. A couple of projects. Here, I want to point out a couple of things. This is a project in Hawaii designed for a peak ground accelerations of 0.6. This is built about 2 years ago it's for the state, but done through federal lands. And this is done by a consultant. It's a consultant design and, contracted out type of project. And they had, on this particular project, they had an option. This was originally a culvert design, either precast or cast-in-place culvert. And at the end, I said, well, it's in 2012. We're right in the middle of all the CDC. I said, why can't we look at a GRS type of structure here? And it was at the end, they were about to award this project. It was a Tiger Grant type of application, which had some really tight time restrictions. So they threw in an alternate. They just said, if you want to do this as a GRS IBS, your contractor can do it, but you have to go and do the design as well. So if you choose to use the GRS, you have to design it, because it was too late to go in and do another full design. The contractor that came in selected to use GRS, and they came in for this. It's a larger project. It was a $25 million project. This component of it was about $1 million of it. So the most of the bids came in at about $1.3 million for this particular part of it. The contractor that won this got it in at about $900,000. So, and they saved about 70 days in construction. So that was a pretty significant finding from that project. So that's something to think about. So that it was the contractor who could have chosen to use either a precast culvert, cast-in-place culvert, or a GRS. He decided to go to GRS, take the risk of doing all the design himself and getting it in here, and still save money. The other thing is, this a couple years later, there's still no bumps, no cracks, no issues associated with the construction of this project. It looks really pretty nice. And this is another cast-in-place structure, by the way. This is the only 2 cast-in-place structures that have been constructed. And if somebody's interested in finding out, this is an interesting story about how they did that construction for this bridge, but don't have enough time to go over that. This is on the I-84 project. High ADT, over 8,000 vehicles per day, 40% truck traffic. Nice smooth across that joint. It's no approach slabs, exactly like all the other projects. Asphalt overlay across that joint, continuous through that joint. And still no problems, no issues. And it's performing beautifully. They're still instrumenting and monitoring. 40% of big trucks coming off that hill. So in others is what I wanted to talk about, some of these items here. But I think we talked about everything in here already except for the age and labor pool. And I don't know what to say about that. You're going to have in certain areas a better pool of people as far as availability of people to work on. But again, you can choose to use a different type of facing element to meet those types of requirements. Hopefully, I've addressed part of that issue by addressing the different types of facings that you can pick. But I will say, the blocks are heavy, but they don't have to move them very much and very far, and it is constructed very, very quickly, even at primarily, we're talking about a small volume of blocks. You're talking a couple thousand blocks. It's not a lot of blocks, and we're building projects are being built that are in the thousands of square feet of blocks like this, and they are constructed with modular blocks, and they're in that depending on the aggregate, specific gravity of that aggregate, and the specification of that block, they're in the 60 to 80, 85 pounds per block. We do have guidance and guide specifications to talk about how to design these things and how to specify these projects, as well as standard plans that will help you in at least getting a starting point. And we can provide those to you in MicroStations or AutoCAD files as well, if you need them. So what are we doing different? What are we going to be doing in EDC 3? Okay, we're going to talk about these topics here real quickly. As far as goals are concerned, we're always going to have numbers to talk about, right? We always want to have numbers. We have about 190, 200 bridges out there right now that are in some sort of, most of them are constructed. There's some in design or some sort of planning stages like James mentioned earlier. But one of the things I want to focus on this particular round of EDC, and I'm going to need your help, the state DOT's help to do this, is to develop some sort of standards so that it's not a unique thing that somebody's, just doesn't have that if they don't have that experience, that they won't be able to try it out because it's not in their standard practice. So what I'd like to see is states working on some standard plans and specifications to consider the use of GRS. So that's what I'm going to be looking for this Everyday Counts 3 as one of my main goals, is try to get this moved away from just one project and done, and it was it was fun, but we'll move on to let's try to incorporate it into standard practice so that other engineers that are coming up later on can say, well, maybe this is something that could be considered on this particular project. And we also want to be able to track some of these time and cost benefits. And I have a contract right now that's collecting some of this information. So some of you or some of your staff may be contacted to help me collect some of this information, because I'm going to have plans, specifications, bid tabs, all kinds of information on the specific projects, and I'm going to make that available to everybody. So so that people can see, hey, I have a bridge that's 40 feet in span and 10 feet high, and it's a grade separation. How many of those types of bridges have been built? Well, I can go to that table and do a sort of that type of structure, and I can say, well, they've built 20 of them. And this is where they built them, and here are the contact information for where I can ask some questions from people that have used them. And here are the plans, and here's the specifications that were used. So that's the type of information I'm going to try to get out there. And so I'm thinking like by early spring, mid-spring 2015, I'll have that information, at least for the projects that are currently in those first 190, 200 bridges that I have. But I'm going to continue that into the future for the next 2 years. As far as state and local transportation agencies, I want to bring on board more bridge engineers and communicating more directly with bridge engineers, working with folks like James and others in different states that have had some experience to help me in sharing their experience with you guys, with everybody else that hasn't had that experience. I also want to work more with consultants and contractors. I was talking with a gentleman over here from ACEC with the consultants group, and also with contractors to try to do some more workshops specifically addressing those design considerations for the consultants as well as construction considerations for the contractors, and try to get that experience built up a little bit more. And obviously training, workshops, showcases, we'll continue to do that as we've been doing them. So let me know if there's something that you'd be interested in or need some additional training for your staff or others in your states. We've done a whole bunch of showcases in the last 3 years, and we already have 3 more planned for 2015, and I'll be looking for other projects to do some additional showcases. I think these are really good opportunities to not only learn a little bit more about the projects, but also get a better idea from people who are using them. And we also bring in the consultants and the contractors that are building and designing these bridges to present during these showcases. So these are really good opportunities to come and see. So if you are interested in these, I'm going I usually send out announcements to the state people that are in that particular state, and also all the surrounding states for these showcases, so people can make them. And we're going to be doing a lot more publications of case histories and papers, and we have a lot of data now on projects that have been monitored and instrumented over the last 4 years. So that will be published here in TRB and the ASCE conferences and the Geosynthetics conferences. And again, standard practice, work with the stick incentive program. You guys all have sticks in your states? Good. This is a great opportunity to work specifically on what I'm talking about, is developing these standards and developing the standard specs and plans for use in your states. So I'll be wanting to talk to you about using these types of resources to help you doing this type of development. The AID projects, we've had, I think, 4 projects, AID projects that have been awarded through AID. Arkansas is here, anybody? You guys just got, yep. You guys just got one project. I just saw an email a couple of days ago. So that'll be a good project to get started on. So, and that, in addition with maybe some stick money, you could use that project to help you develop some of those standard practice. So, you know, we went over this morning. Here's just a review of this information. But basically, the STICS incentive program allows you to develop these standard practices for your state. The AID program allows you to award projects or to fund the construction of these projects. Okay? So you can use both of these resources to help you implement the technologies, not only the GRS technology, but all of the EDC technologies, as well as some of the Sharp 2 stuff that's going on. Okay? I'm going to leave this question for the end, just because of our time. I wanted to get to these example projects because I think that it's important to get to this. You'll note in these projects that there's lots of different types of crossings, from water crossings to trail crossings to roadway crossings and so on. Many different types of superstructure. It doesn't matter what type of superstructure you want to design. You're the bridge engineer. You design whatever type of superstructure you feel comfortable with. You have 4,000 pounds per square foot size, your bearing area, your width to meet that 4,000 pounds per square foot based on your structure loads. Okay? That's what we need. Different geometries, skews, supers, elevations, crowns, all kinds of different geometries have been done. Different facing types, we talked about that already, different types of fill materials, geosynthetics from geogrids to geotextiles, in-house or consultant design, you know, built by in-house forces or by contractors. So lots of variability in the way that these projects can be done. This was the first one that was constructed in 2005, and since then this project has been working very, very well. Has had no issues at all, has no cracks, no bumps, no anything on that asphalt approaches. And that's about an 80-foot span with prefab bridge elements for the prefab boxes. In New York, you can also do some structures behind existing abutments, which is another really interesting approach. There's been several projects that have gone this route. Michigan, anybody here from Michigan? On their project, your project, they were doing that. On your project, they had a existing abutment in that construction. Although one existing abutment on one side ended up falling in when they excavated it out. So I'll show you a picture of that, but they fixed it.
Yeah, that was some of the challenges there with getting the sheeting in around it.
Right. So they ended up replacing that with some sheeting, that old abutment. So this is a project in Pennsylvania. So this is a timber type of superstructure. Yeah, see all the riprap, you end up, basically full channel riprap at that when you're this width. This is James's Bridge. Some other projects in Delaware, fairly tall structures here. Again, fully lined channels, fairly large riprap for the type of flow that you're dealing with, and they've had some significant flows already. Project in South Dakota. Anybody here from South Dakota? No? Well, here's your project. But again, this is a fairly fast-moving creek. It's about 10 feet per second on this project. But they've done all the hydraulics. They've done all the analysis for this project. Project in Hawaii. Is a project from federal lands. They did another one very similar to this that was done in Nevada as well with federal lands. And steel with a timber deck, but building behind the old existing abutments. Project in Montana, Maryland, one of the projects in Oklahoma that you guys did. I don't have a finished photo of these projects. They built 4 on this particular alignment. They were right next to each other, basically crossing the same creek over and over again. But I think they chose to use 4 different types of superstructures for each one of the bridges. And they were doing that in order to kind of test out different types of superstructures and how they behaved and how they were constructed on each one of them so that they can learn from that experience. This is during one of the showcases. This is that Michigan project. And this is where the old abutment was. It just collapsed it was in such bad shape, it just collapsed when they excavated it out. And they ended up replacing it with some sheet pile. The other side is the existing abutment, but on this side it's got some sheet piles. I think you guys ended up using some articulated concrete blocks for your scour protection in the channel as well. Nebraska. This is a trail. This is an old railroad line that converted to a trail. No water issues at all in this type of situation. These are great applications. They're easy. It looks good, and fairly tall, visible structure, and it's performing really, really well. This is steel superstructure with a composite deck on top of it. Semi-integral abutments at the end. South Carolina, Washington, Florida. Again, this is a real nice finish on this road. No approach slabs, just jointless structure right across there. Another railroad crossing. These are great opportunities. If we can work with the railroads and have them allow us to do these work really, really well in these applications. There's another railroad crossing in Massachusetts. It's finished now, I just don't have finished photos. A steel structure, semi-integral abutments. This is about a 100-foot span. We're heavily instrumenting this for the thermal impacts on this structure. And it's got a fairly heavy, steep skew. It's about a 35-degree skew on this structure. This project in Puerto Rico has about an ADT of 40,000. So lots of traffic, lots of load. And this is the project here in Montana. These large wet cast blocks here. So here's our team that's involved in working on this. So all of this is on your thumb drives that they handed out. So that's why it's important to just point this out. But contact myself or anybody else if you have any questions. We have some folks that are in the bridge engineering group, our hydraulics engineer, and the rest of us are geotechnical engineers working either at headquarters or in the resource center or in our research office. Lots of more information available in the EDC website. And that's it. Any other questions? Were there any questions out on the web? Okay. Any other questions here? Yes, sir.
If you have a multi-span bridge and you're a little concerned, instead of having to bump at the end of the bridge, you have the rigid piers. Seems like to me there should be a limitation on the amount of differential deflection. Is there any guidance along those lines?
The question has to do with the differential settlements associated with multiple span structures. And are there any guidance to that? Primarily, I'll just say that our guidance is to focus primarily on single span structures. Okay, most of the bridges have been single span structures. There was one that was constructed with a 2-span structure in Colorado in 1999, and it's still working really well. There's this one in Maine that was constructed as a 2-span structure, and it's working very, very well. And there's a new one in Colorado that's a 3-span structure that the abutment is on GRS, the piers are on drill shafts. What they are doing is they are overbuilding the abutment so that they can accommodate that settlement, and the foundation of that abutment is on bedrock. So they're only looking at that compressibility of that embankment fill. So they can anticipate how much settlement they're going to get so that they can end up at the elevation that they want to end up. We don't really have any specific guidance on how to do that because we're primarily trying to focus on single-span structures. But if you want to do a multiple-span structure, I'm not going to tell you can't do it. It's just I'd say let's talk about it more. Let's talk about it, about the site a little bit more and on the design, because we don't really have any guidance other than you need to consider that differential settlement. We don't want to have a bump in the middle of that bridge, okay? We definitely don't want it, because we are going to get that settlement, right? And we don't want to get that reverse moment in that structure, right? So we want to make sure that we account for that, and we don't want to create a problem in that way. So that's why we're trying to focus and maintain it as a single span structured project or product for now. I think we're good. Oh, go ahead.
Have you seen any issues with clogging of geosynthetic reinforcement of the open graded drainage course with fines, plugging that up and creating drainage issues?
The question had to do with clogging of the geotextile due to fines coming into the fill, draining through that open graded material. Well, water, as it's coming in and coming out, it washes through that fill fairly quickly, and the fill is very, very porous. So any fines that come in there really cannot stay in there. There's enough flow through that fill that they won't stay in that fill. If they do come in, they won't stay in there. But we haven't seen any material coming in. But we're not using that fabric as a drainage medium. We're using it as a reinforcement application. So we're not really looking at its permeability or permittivity that we would normally look at from a fabric in a hydraulic sense. We're looking at only the strength properties of that material and stiffness properties. Okay, I think we're good. Thank you, everybody, and you have my contact information. Let me know if there's any questions.